With that, I'll introduce Mats now. He's a Chief Commercial Officer and one of the 3 founders of Bleu Technologies, a Danish methanol fuel cell developer and manufacturer. And Mats has been working in the fuel cell industry for the past 15 years with a background at Schneider, at Ballard and at Serenergy. He led a project back in 2015, launching the first methanol fuel station in Europe, and has been involved in numerous development projects around the world, built several vehicles and vessels with global OEMs. And he sees great opportunities for methanol fuel cells for a large variety of applications. And with that, Matt, I hand it over to you.
Thank you. So thank you for the invitation to give a quick talk here about methanol fuel cells, the status, where we are, and how the development we see it in the future. Methanol fuel cells can be done in many different ways. There are some different technologies, fuel cell types. The one I will be focusing on is the PEM type fuel cell and the high temperature PEM type fuel cell with an external methanol reformer. So this means methanol is reformed into hydrogen, and this hydrogen is then converted into electricity in the fuel cell. When using a methanol reformer, there is a limitation as to how fast you can dynamically change the load points of the fuel cell. So mostly when dealing with reformed systems for fuel cells, you would also have a battery system to take care of the peaks in any different application. So that's an intricate part of having methanol fuel cells, is some kind of hybridization mode. As a company, Blue World are focusing on many different areas, primarily automotive and mobility solutions, so land-based transport. Also some other areas where you can replace a typical combustion engine with a methanol fuel cell, and then the heavy-duty segment, where the maritime area is regarded as that. Main point is that we can reduce CO2, remove harmful emissions, and save some cost due to a higher electrical conversion efficiency in most engines. So the high temperature PEM technology is a little bit different than other types of fuel cells, the traditional low temperature PEM. Now, the big advantage of high temperature PEM is its elevated operation temperature. It's operating at around 160 degrees. This means that the waste heat from the fuel cell has some potency, and it can be used to evaporate the incoming fuel. The incoming fuel will be a mixture of water and methanol, and this can be then evaporated by the waste heat, meaning you save some net energy in that total conversion in a system. Once the gas has been reformed in a generic or normal situation, if you want to use other fuel cells, you need to clean the gas. The carbon monoxide in the reformed gas is not acceptable to especially the low temperature PEM type fuel cell. With high temperature PEM, it is acceptable. So this means the simplicity in the system design is very high because there is no need for gas cleanup. So these things all put together means that the overall system is a very simple one, and you have a high net electrical efficiency because you can reuse waste heat streams and waste gas streams inside the fuel cell system. The mixture of water and methanol, giving the right steam to carbon ratio to work in a reformer, is around 60%. The reason we illustrate 100% methanol going in here is because we can condensate the water from the fuel cell exhaust, so we can basically generate our own water for this. So it's a water neutral system. So as a company and as a manufacturer, our key focus is the fuel cell stack and the components inside that. We also do design the reformer, but it can be manufactured many places. It's a relatively simple manufacturing methods. And this constitutes a product platform, which can then be used in multiple applications with some variance as to how you build the system, how big the system is, and how you operate it, etc. One thing to note here is the startup time. So unlike a typical hydrogen fuel cell, which has a very short startup time, a high temperature PEM reformer-based system has a longer startup time. So this is something to take into account when doing an overall system design. So this is also why a battery hybridization makes sense, because the battery will not only take the peak loads, but also the starting load. This is specifically interesting for vehicles, but to some degree also for the maritime applications. So this is how it looks on a typical vehicle. And I'll take the basis of this, although this is for the maritime use. This is sort of where we're coming from as a technology provider. And it offers many of the same things as a traditional combustion engine. But this is with zero harmful emission and significantly increased electrical efficiency coming from the generating technology. In terms of emissions from the fuel cell, as I said before, the CO2 emissions coming out of the fuel cell will be the same as going in. So the chemical bound carbon in the methanol will be released again. That's not really easy to change. What is, on the other hand, something that's different from the traditional combustion engines is there are no particle emissions, no NOx, no SOx. It is a completely clean emission. So this means that we will not live up to regular emission standards. We live up to what WHO has of guidelines for workable breathing air. So this is you could say the big advantage of going fuel cells. So when we are looking into this, we have built up a product concept around our core components, the stack and the reformers and related components. And basically, this is sort of a modular approach to this. This is pretty regular when it comes to fuel cells in general, but pretty special when it comes to methanol fuel cells. So it's a modular design like you would see on batteries, because it's a cell-based technology. It can go up to 5 megawatts and beyond. It has a high electrical conversion efficiency compared to reformed fuel cell systems in general. It is very easy to integrate. It is, if you put these systems in a total scale of 5 megawatt, you can distribute it around any vessel. It fits into many different places. The input is methanol, and the output is electricity. And there is a cooling demand, of course, but it is relatively simple to integrate into larger cooling systems. When it comes to one of the barriers of implementation, it is always a matter of cost, and the fuel side of things will be covered by somebody else but me, but it is relatively simple when it comes to methanol, unlike hydrogen fuel cells, where the fuel storage on board, being pressurized or cryogenic, is costly and has many considerations to take into account. When it comes to the capex, or the cost of this equipment, we can get into parity with a combustion engine. That is what we see, and that is in our roadmap. It's not next year, but it is what is possible. We see ourselves as being part of a larger setup, and so far it's not very clear exactly which vessel type will have the best use of the benefits a methanol fuel cell can give. This is something we're working on. We see this as being part of the APU for larger ships, being part of the propulsion system for small ships. And inside a fuel cell solution, you have both thermal systems and you have the fuel converter or the reformer, which has a catalyst, a methanol catalyst inside. And then you have the fuel cell stacks consisting of MEAs and flow plates. And all of these things and the systems that is needed to actually get this solution to work is what we are focused on. here's just an overview of the different applications beyond maritime where this technology basically have its synergies with. So we are also working on these other things, but it's a generic technology platform that can be used across this. At the end, one of the key points and bottlenecks that is needed both to supply into the market, but also to get a good quality and a good price, is the mass manufacturing of the core technology. Maritime cabinets, power electronics, that kind of stuff is not unknown, so that's possible to do. What is key here is the new stuff, and that is producing membrane, electrode, and flow plates in sufficient good quality, which has a sufficiently high volume and good price. So in Denmark, in Aalborg, we are setting up a pilot production which can give a decent capacity and get us to a good starting point. And we're planning a large-scale manufacturing unit which will be able to provide this in very large volumes. And that is the key to making it competitive. And that's my bits regarding this.
Great, thank you very much, Mats. So we do have a couple of questions for you. Maybe I'll start with the gas cleaner that you mentioned. That was a bit unclear to a number of the viewers. So could you elaborate on what the gas cleanup actually means?
Well, that means basically making sure that you do not get carbon monoxide or CO into the low temperature PEM. So it's an element that we don't use. The reason I mention it is because this is normally used in methanol reformer systems using low temperature PEM, which is something we don't need. So there are different ways. There's a palladium membrane, there's a PSA, there's different technologies to do that. So it's not impossible, but it is just a piece of equipment you need, something that has a durability aspects to it as well.
Yeah. So a piece of equipment that you actually don't need.
Do not need. Yeah, exactly.
Yeah, great. Then we have a question on the required fuel purity. Are there requirements for the methanol in terms of purity before it can be used in the fuel cell setup?
Yes, we need the IMPCA standard. So
the chemical grade standard, yeah.
Exactly. So that is what we need. There are a number of fuel processing setups we can implement before the fuel cell system, which would enable us to do worse qualities. We don't mind water in the methanol. The challenge comes a little bit when you don't know how much, etc. But that is also possible to basically take raw methanol on board. So that's also possible.
Yeah. Okay. Then we have a question concerning material availability. So if you're talking about PEM technology, there's a bit of a competition also between the fuel cells and the electrolyzers, both using PEM technology. So do you see issues with material availability?
So we use platinum, and there is a good availability of platinum. Plus, we can you could say recondition the fuel cells when spent. So we get all that platinum back. So it's a fixed resource.
Okay. Then we have a question on the fuel cell racks you mentioned on how scalable and modular they actually are.
Mm-hmm. So basically, these can be installed in ones or in manys, and up to 5 megawatts. But that's fundamentally not a limitation as such. So you can set one component in and then connect that to auxiliary systems to actually operate that one block. Thanks.
Then we have a question on bus application. So city buses, intercity buses. Would it be interesting to compare the methanol fuel cell solution there with a hydrogen fuel cell and batteries from the perspective of cost of ownership? Do you have any view on how those would compare?
Yes, it compares very, very well. So it is a very competitive technology due to the relative low price of the fuel and the infrastructure. And if you do the design of the bus in the right way, so making sure that you combine the batteries forces with the fuel cell forces, you have a very, very competitive bus topology there.
Yeah. Then we have a very basic question on the product you actually produce when you convert methanol to electricity. What's the main reaction product? So a question about CO2 neutrality. What happens to the carbon atoms?
Well, they go out. So if it is fossil carbon atoms, they will come out again. So of course, if this is needs to be sustainable, the carbon sources also needs to be sustainable. So that comes back to the whole question: will we have enough carbon? Now that's a big discussion. I don't think today is where I should take that, but I would say based on what we see, even without direct air capture, is that we have plenty of carbon sources available.
And then just to check up on that, it does convert fully to CO2. You don't have a CO stream in the exhaust?
No, as I said, is that we do accept the CO from the reformer to the fuel cell, but after the fuel cell in these so-called anode waste gas, we convert the CO that can go through the fuel cell into CO2. Yeah. So there are no CO coming out of the exhaust.
Yeah. Then we have a more critical question zooming in on the efficiency you mentioned. You mentioned 50 to 60% efficiency, but then again, two-stroke engines for shipping, that's the same type of efficiency they get to. So a question on how you position the fuel cell system versus the combustion engine running on methanol.
Yeah, so what I tried to show with this slide that I have here is that the main engine, a two-stroke engine, is not something we compete against, basically. So we are more against the four-stroke APUs. And you could say if you do this really well, it is also on par efficiency-wise. So we are talking, if you have no value from the added benefit of the product we supply, then don't buy it.
Yeah. Basically. Okay. Then maybe a final one, but also an important one, I think. A question on the durability. Do you have an insight into the lifetime of the fuel cells?
Yes. So the technology platform that we have, we know is good for beyond 20,000 hours. Now, doing that in a product on a ship is not something you prove overnight. We don't have the luxury of producing this for many, many years. So it is not so much about technical capability as it is about developing the product and proving it on the sea. So we foresee that this is very possible because we know the technology can do it, but it will take some time to give out warranties of the same.
So stay tuned for that one. Yeah.
Yeah, exactly.
Great. All right. Thank you very much, Mats, once again.